Today we have a talk from Professor Katie Driggs-Campbell. She is currently an assistant professor at the University of Illinois Urbana-Champaign in the Department of Electrical and Computer Engineering, with a courtesy appointment in the Department of Computer Science. Prior to joining Illinois, she received a BSc with honors from Arizona State University in 2012 and an MS from UC Berkeley in 2015. She earned her PhD in 2017 in electrical engineering and computer science from UC Berkeley. After that, she was a postdoctoral research scholar at the Stanford Intelligence System Laboratory in the Aeronautics and Astronautics Department. Katie now runs the Human-Centered Autonomy Lab, which aims to design safe autonomous systems and the robots that can safely interact with people out in the real world. Her work draws from the fields of robotics, learning, decision-making, control, and human factors, and is supported by the National Robotic Initiative 2.0, USDA, NIFA, plus NSF AI Institute, and industry collaborators in the manufacturing and automotive domains. Katie is the recipient of the NSF Career Award and is also leading the UIDC Joint Research Center for Cyber Physical Manufacturing Networks. And today's talk will be devoted to the tools for interactive autonomy, modeling, prediction, and inference. So please join us in this nice talk.
Awesome. Well, thank you so much for that introduction. So first off, thank you so much for having me. I'm super excited to chat about some of the stuff that we've been thinking about and some of the things that we work on in my lab. If anyone has any questions throughout the talk or anything like that, feel free to unmute yourself, or I'll try to keep an eye on the Hangouts as well. Although I haven't used Hangouts or Google Meet in a hot minute, so I'll try to sort of keep an eye on things here. But don't hesitate to interrupt or ask questions. We can try and keep this fun. So I guess first off, let's make sure that little blip. All right, so again, as was sort of mentioned, so today we're going to mostly be talking about different ways that we can model and really think about people, so we can enable more interactive autonomy. And for the most part today, I'll be presenting work by Zhe Huang, who is actually, I believe he is in the audience. This is one of your interns and one of my fabulous students, as well as Masha Itkina, who's a recent graduate from Stanford and now moving on to TRI. Okay, so first, for a little bit of background on who I am and just sort of how I'm going to be thinking about things. Broadly speaking, my lab tries to think about how we can design autonomous systems that operate out in the real world with people. So we pull from a lot of tools from AI and optimization, as well as decision-making and controls. We can deploy these systems and really think about how we can understand the people that are going to be using them, operating around them, and sort of subject to the whims of the autonomous systems that we're designing. So we really think about how we can make humans sort of central to all the things that we do. One of the things that's very important to me is making sure that we try and make things as realistic as possible. So we do always try to make sure we have some sort of real world deployment or something that's sort of there and physical, sort of a real embodiment. So hopefully when we combine all of these things together, we have sort of our nice formulations, our real world testings, we can think about deployment, and hopefully everything that we design is going to operate the way that we want it to, and sort of the ways we expect. So this is sort of the grand scope, and within this, so we look a lot at things like safety. So how do we validate these systems? Decision making, again, how do we make sure that these systems can do the things that we want them to do? And again, looking at these sort of aspects of people. So really making sure we can model and understand what they're going to do. And again, this is sort of going to be the focus of what we talk about today. And we'll be mostly focusing on things surrounding vehicles and whatnot, but we also work on a lot of other things in my lab, like mobile robotics that work out in the field, sort of embracing the Midwest agriculture aspects. We look a lot at crowd navigation, so really thinking about how we can have a little bit closer coupling between things, robots working around people, of course, vehicles and cars, and then also some manufacturing applications. But again, today we're mostly going to be talking about how we can sort of model and understand humans sort of in the context of autonomous vehicles or things sort of around the transportation realm. Okay, so first off, let's sort of take a step back and really think about sort of what we want when we're trying to design these systems that should be operating around people. So let's just say we want to make sure that our system is safe and operates robustly in whatever environment we try to deployment. So we want to safely and effectively control our robot. And we want to do this despite uncertainty and disturbances. And these uncertainties and these disturbances could come about by people that are going to be operating around this. This could also be something a little bit more mundane, just like the uncertainty that is in the world. But if you were to sort of cast this problem as sort of a traditional robust control problem, you try to sort of write it out or write an equation that's something like this here. So hopefully everyone can see my mouse. But we have the state of our system that we're trying to control. We have some known dynamics describe our vehicle or whatever our system is. And we basically want to find this controller that will help us try to get this system to actually do what we want it to do. And again, we have these disturbances or this uncertainty that classically is basically represented as this generic function that is added onto the right side of this equation here. So this can be a function of some uncertainty, it can be a function of the state or whatever input you're doing here. And typically this is sort of a classic problem that is well understood and well solved by the control community. And traditionally it was really looking at these sorts of problems where we have some sort of sensor noise or environment uncertainty. We kind of have a good handle on sort of what these signals are. So if we have some perception uncertainty, some uncertainty and sort of our precise localization, this is sort of the task it was meant to handle, where we sort of have this well-prescribed noise and uncertainty, and we want to basically be robust against these sorts of situations here. But more recently, this sort of formulation and this sort of take on things has become sort of more apparent, or sort of has seen a bit of a revival, as it can also handle things like model mismatch. So if you have some things in your dynamics that maybe you couldn't model or you couldn't quite capture, or maybe you just have some gap between some simulation that you're running and the system that you actually want to deploy it on, this sort of model mismatch is also well captured by this. So this has been expanded to things like adversarial RL, and basically anything that sort of looks at this like sim to real gap is basically trying to capture some of this model mismatch and whatnot. So this sort of robust take on things allows us to do a lot of really cool things, and again, sort of help us deploy these systems out in practice. But one thing that this sort of approach doesn't really handle well is some of these longer term interactions. So when we really think about some of the uncertainties that come from sort of more sequential, again, these longer term situations, for example, a human driven car and a autonomous driven car sort of interacting, a lot of these sorts of interactions where you could have multiple things that sort of compound, or some things that sort of affect, again, these sort of long-term issues, it doesn't really handle these sorts of things well. So if we really want to make sure that we can robustly and effectively control our vehicle, or do this in a safe way, we need to make sure we can handle these longer-term interactions and whatnot. So one of the ways you can solve this is by trying to look a little bit more carefully at how you model and predict that human behavior and whatnot. So that's sort of the key motivation here, and what we'll be talking about for the most part today is how do we actually get these sort of longer term predictions, and how can we incorporate this into our autonomous stack so we can have this sort of safer and effective control here. And to just sort of further motivate why we sort of need to have a good understanding of the people, we'll take a quick aside, a quick step away from an autonomous vehicle example, but we can start looking at some of these trade-offs that we might have when you have some robotic system and some human interacting and whatnot. So one of the problems that you have is you sort of have this inherent trade-off when you are interacting with a person. You want to guarantee safety, and you want to have this system that is efficient and effective at what it's actually trying to do. So for example, here we'll have a simple case where we have a robot manipulator interacting with a human. So the human is going to be performing some task, the robot is doing its thing, and it has sort of a purely safe controller. So it will automatically stop whenever the human is detected. This is sort of the default sort of optimizing just for safety in your process here. So we can see we have a very safe system. It will automatically be safe. It's not very interactive though. So we're kind of lacking on this thing. We're not really leveraging any of the aspects of the robot and the human sort of working together here. And it's sort of efficient. Although we can see that as we start doing things like moving faster, and in certain cases, we can still be very safe, but we can really sacrifice efficiency here. So when the human is moving very fast or is moving in a particular way, we're basically really limiting the interaction here, and we're really suffering inefficiency. So the robot just sort of freezes here. So again, hopefully by really looking at how this human interacts, or human moves, thinking about interaction a little bit more carefully, we can start thinking about how to balance these things. And this example, again, is sort of a specific to a manipulator case, but you can also see similar things in, say, autonomous driving, where you're trying to understand what the people are doing. You can kind of get into these sort of freezing or deadlock zones if you don't really account for the human and sort of what they do here. So again, taking a step back, we're just trying to think about some situations where we're trying to think about where and why we might want to model the human, and how we can sort of leverage some of these insights to sort of try to maximize efficiency and safety, and hopefully have nice sort of interactive systems as well. Okay, so one other sort of thing I wanted to mention here, sort of just sort of give a big picture overview of, is when I say we want to start modeling the human, or we want to incorporate some different models into our control pipeline, depending on who you ask, that could mean a variety of different things. So if I say human modeling to someone who specializes in human factors, they could be thinking about modeling the human maybe inside the car. They could be thinking about distraction or attention. This is sort of one class of human modeling. We can think about this in terms of generative modeling for things like traffic simulation. There's sort of a whole realm of things that this could mean. So we can try and sort of codify and sort of think a little bit more concretely about what this is. So we're going to take a quick aside to just, try to make sure we're all on the same page here. So typically, if we want to think about something like human modeling, we can basically break down a set of tasks. We can kind of think about this as basically an evolution of states. There's something about this human that we are trying to sort of monitor that evolves over time. We have some observations of sort of what this behavior is, but there's basically some hidden variables and some sort of latent parameters that are also going to drive and affect sort of what this human is actually going to do. So this is going to affect the decisions and the control actions that this human makes, and this is going to change how these evolve over time and through the whole scene. So for example, in the traffic case, every agent is going to have some parameters, some things that are guiding it, and this is going to affect how they maneuver over time and whatnot. So again, taking a step back, thinking about some of these canonical tasks, one of the things that we've tried to do in the past is try to basically codify some of these canonical tasks. So we can think of this in terms of state estimation. We can think of these things in terms of intention estimation. So again, this is thinking about what are the goals, or sort of what are the driving forces of the human. What are some of their traits? So what are the things that sort of determine how they're going to actually execute some actions? And then we can also sort of separately, or hopefully in tandem with some of these things, connect this to motion prediction. So actually think about how they're going to maneuver in the future. So a lot of these things sort of combine things like inference. So you're trying to estimate sort of a current state of things, or your sort of current best guess of these different parameters, and then hopefully propagate this into the future. So think about some prediction here. So for each of these different sort of tasks and whatnot, there's a number of different things that we want to consider though. And these are sort of things that we'll touch on throughout this presentation, and hopefully we can have some discussion at the end sort of about the impacts of these. But the first is really thinking about the space that you want to operate in. So really thinking about how you're defining your problem and sort of what is the scope of what you're thinking about. How are you going to represent some of your uncertainty, and what is the inference or prediction paradigm? So just to give a little bit of examples of things that I mean when I'm talking about this. So for example, if I'm thinking about something like intent estimation, I can sort of think about what this sort of space means. So when I'm saying I have a model that captures some intent of the user, what does this mean? So typically this is something that is defined explicitly depending on sort of your problem and your specific use case. These can be things that are defined by a route that you're trying to take, or some like high level action. So for example, you can think of things like lane changes or lane keeping as different modes of intent. You can also think of these things as goals that sort of change over time. But this again is something that you sort of have to think about when you're thinking about your specific example. As another thing that you could think about is the actual representation that you're going to use in, say, your prediction pipeline. So this is something that we'll kind of come back to towards the end of the presentation, but basically how you want to represent this and what is sort of useful for your downstream tasks can affect the tools that you use along the way. So for example, there are many different design choices that you could make. For example, the most common, I think, approach when we think about prediction is trying to get a single trajectory. There's many different ways you can come up with this, but I'm trying to come up with a sort of single output here. You can also think about this as more of a distribution over possible trajectories, or you can think of these as sort of more set-based type predictions. And again, how you represent this, again, informs both your downstream actions that you can take when you are tying this back to your decision-making and control scheme, or it connects back to basically the tools that you can actually use when you're actually doing this prediction here. Okay. So again, just sort of tying things back. So again, we've been talking about sort of leveraging human models in deciding some of these, in incorporating or taking some of these human models to sort of incorporate these things into our decision making and control. So hopefully we can have this more interactive and sort of hopefully better autonomous agent here. So again, some of the things that we'll touch on in the next little bit is really thinking about how the space and how we sort of define and represent our system is going to sort of impact what we do and how we can sort of take some cool representations and hopefully do some interesting things with it. And also we'll try to see if we can link some of these things together. So instead of treating these as sort of separate models that maybe have different use cases, seeing if we can incorporate these things together. So a little bit more concretely, first, we're going to be talking about intent-guided motion prediction. So seeing how we can come up with a unified framework to try and incorporate intent into our prediction paradigm. And hopefully a very intuitive way. So leverage some of these ideas from inference to help inform prediction. And then depending on time and whatnot, we'll talk a little bit about spatial inference. So instead of thinking about how we sort of propagate things forward in time and how we can model human behavior in time, how we can make some inferences spatially using some different representations like occupancy grids. Okay, so unless there are any questions or comments, and again, I can't see your faces, so please just speak up if you do have any questions. We'll get started with our first topic on intent-guided motion prediction. And I will apologize for anyone who was at ICRA. This will be a little bit of an overlap, but I only have so much to say in a month. So we'll start with some of this work. All right. So. Okay, so when we talk about, so we're going to be, again, focusing on motion prediction. So again, thinking about how we can understand how people are going to maneuver through space over time. There are sort of two different ways we can start sort of classifying or codifying or thinking about this problem. And sort of the canonical divide is thinking about this sort of physics-based method or a model-based approach and a pattern-based or more of a data-driven type approach. So if we think about this sort of physics-based model, we have some sort of known way we want the system to maneuver through space. We want to sort of come up with some dynamical model of the agent where we have its states. We want to sort of estimate its inputs and see how this guides or sort of pushes this human motion. Maybe we have some uncertainty, but we're basically going to propagate this forward through time in a relatively known and more structured way. So we sort of assume that this is the thing that we're trying to learn. And again, we're sort of going to impose some structure on this to try and match what we observe of human behavior. On the other hand, this is sort of the more popular approach these days. The more pattern-based methods are basically trying to do the same thing, but instead we take a sequence of observations and we try to estimate what the most likely next state is here. And both of these two sort of methods have their pros and cons. Here, one, we have a lot more insight because we're adding the structure. We're sort of adding some understanding of what the humans are doing and how they're going to behave, versus more of the pattern-based where we can capture some of the more nuanced motion. We're not really limited by the structure that we're imposing here, but we don't have sort of, again, that same sort of insight, so we can't make necessarily any guarantees and whatnot. So each of these sort of have their importance, and sort of one of the things that we're going to try to do is try to see if we can sort of merge these two ideas together, or take some insights from each of them to hopefully come up with something that is sort of has a good balance and sort of, again, combines the best of both worlds here. Another thing I had mentioned before is one of the things that we wanted to try and do is try to combine some of those ideas or different types of human models that we had talked about before. And one of the things that we're going to try and pull from is this idea of intent-guided prediction here. So we want to, again, think about how we can incorporate intention into our prediction to hopefully make things a little bit more stable and hopefully perform a bit better. And there's lots of motivation to think about intent, especially from a human perspective. So typically when we as people observe human motion, we don't really care too much about the surface behaviors. So when you and I, even if we're talking fairly technically about the movement or the motion of some agent, chances are when we talk about it, we're not going to be talking about in XY positions. We're going to be sort of abstracting it and talking about it in some sort of higher level. So intentions really determine how we understand, how we recall things, and how we're going to react and sort of predict these behaviors and whatnot. So when we think about these sort of intentions, again, this is going to be some sort of abstraction that sort of helps us with the reasoning process and whatnot. And so there's lots of sort of very intuitive examples in the autonomous driving case. For example, in lane changing, we can sort of really easily think of these different high-level actions. Again, for example, lane keeping for lane changing. And one thing that's sort of interesting is that typically when people are observing things like continuous motion, so for example, this car driving, people typically have a pretty firm agreement on where these sort of separating boundaries lie. So where these sort of different high-level actions are with pretty good reliability, and also in the future. It's not necessarily sort of retroactively saying, okay, this is where these things happen, but there is also some sort of predictive capability here as well. So there's lots of sort of motivation and reason for thinking about why we can incorporate intent and whatnot. And again, hopefully we can start thinking about how we can tie this into prediction and whatnot here. And the way we'll be sort of thinking about intention and the rest of the talk for now is sort of what is the goal of the agent? So what sort of action or what sort of position is it trying to ultimately achieve? Okay, so as another sort of little bit of example here, so we'll be focusing on pedestrian motion prediction here. And again, we want to think about how we can start incorporating intent into these predictions here. So if we were, say, going to observe human motion here, so we observe some human motion, and if we were just going to predict where this pedestrian was going to go, likely many of us would just do something, have some prediction just like this here. Typically, this is a pretty good a good prediction. People tend to sort of like taking, following the principle of least action. We tend to follow sort of relatively straight lines and whatnot. So this seems like a relatively reasonable prediction given the information that we have available to us now. But if I were to sort of give you some additional information, like say there are some potential goals or regions that the person might be targeting, this would probably significantly change how we estimate sort of what this person is going to do moving forward. So for example, if I set these 3 goals out, we might have slightly different predictions, like saying they will actually go to their goal. So it adds some constraints, it adds some different insights here, and this again dramatically changes what we're going to do. So we're going to start thinking about how we can sort of take this goal-oriented or intent-guided prediction and start sort of piecing together how we can fit these things together. So this basically brings up 2 different problems here that we need to address. So first, how do we infer this human's intent? So how do we sort of estimate these goals? And then how do we use it to predict that future trajectory? So these are the 2 problems that we're going to try to solve and hopefully try to address here. So the way we're going to solve this is by looking at a common inference framework with particle filters. So for those of you who are not super familiar, particle filters are a very common filtering method. And the basic idea is we want to sort of take a bunch of particles that will represent our agent, and we're going to basically try to propagate them forward, see which ones are sort of the most likely or the most promising particles, and these sort of become the dominant one. So typically this is something that is used for things like localization or state estimation and whatnot. And we're going to sort of combine this to simultaneously use this to come up with a good prediction, as well as help us estimate our intent here. So the way we're going to do this, we're going to start with our particles, and we're going to assign each of these particles one of the different goals or modes of intent that we have. So we'll assign each of these sort of a different intent here. We observe some motion of that human. So we observe them for some time window here. And what we're going to do is we're going to take each of our particles at this initial position, and we're going to propagate them forward in time. So right now we're assuming that we have some sort of generative model or something that can give us this forward prediction, which we'll come back to later because that gets to our problem 2, I believe. But assuming that we have this, we propagate this forward in time, and we basically then are able to see which particles are most representative or most being best represented or representing our observation best. And then we update our particles here, and we do our sampling update then. We have this mutation property, which we'll talk about in just a moment here. But basically, once we have these particles, we get this new distribution over the intents. So we're basically able to sort of understand which mode is more likely. And again, we can associate this with a future prediction. Again, reflecting the different modes of intentions that we could have. So the one thing to note here is we do have this mutation, which I sort of skipped over before. But one thing that we introduced here is this small probability of these particles basically changing their intent at some point. So this is good for sort of two reasons. So first off, typically when you're trying to do inference, you're working on a static problem. So for example, if I'm trying to estimate something that's sort of like fixed, like whether or not a door is open or closed. This is sort of something that it is what it is. There's sort of no change. So when I'm sort of doing this recursive reasoning, I can sort of confidently say, hopefully one thing comes up and I get the sort of probability 1 that this event or this sort of state has been achieved. But typically when we're working with people, we don't necessarily have this sort of static type problem. So we want some sort of liveness property. We want to basically always have the case that 1, we could be wrong, or 2, that the human could be changing their mind. So we want to make sure that these sort of particles don't necessarily die out. So again, it sort of helps keep this liveness. So let's look at a little example and actually show how this will work. Again, right now, we're just sort of assuming that we have this sort of forward model and we're able to sort of predict this, this behavior in the future here. Okay, so here we have our pedestrian who's walking along. We have their sort of observed trajectory up till now, up to this point. And we have these sort of trajectories that are sort of coming out that are going to be our likely prediction of of these future behaviors. And you'll note that they are sort of constrained by this goal or the intent of the person. Over here, we have the basically the likelihoods associated with each of these modes of intent. And you can see at this initial point, we have a small piece of observation, but they're basically all the same. Blue is slightly higher, so these are the trajectories that we're showing. And as we sort of gather more data and observe what's happening, we can see we sort of have this one more dominant intent that arises, and we sort of observe this going through time. And as this person slowly reaches their goal, this is an example where we'll see them sort of change their mind, sort of change their decision. And because we have this mutation property, and again, this sort of liveness piece, we'll actually be able to capture this, this change here so we don't kind of get stuck in this mode. So we'll see that in just a moment here as that person starts sort of walking away. Again, we gather more information. We have some evidence that this that previous estimate was no longer valid. So again, just to sort of show what this looks like, typically if you don't have that mutation, you'll have this sort of case where the particles will die out once you become very confident of your particular mode. So even when you get a lot more evidence, it's basically very hard to change this. By having this sort of mutable component, again, you kind of keep this liveness property so you can have this sort of switching and whatnot. Okay, and so up till now, we've been looking at this sort of simplified case again, where we've been looking at these sort of three very distinct goals. I'd like to note that we can actually make this a lot more complicated, where we can, again, look at many different goals and sort of more finely discretize the space and whatnot, and this still works very well. And this is one of the nice things about particle filtering. Typically, it's something that scales very well as long as you have reasonable computation to do this sort of propagation step and whatnot. So again, this is sort of a typical framework. We have some sort of interesting properties in mutation, which is good for human behavior. But now we need to sort of actually talk about how we're actually going to get this. Now, on some level, if you have any generative model or any good prediction, you can sort of fill this in with whatever your favorite prediction method is now, as long as you have something that can basically be conditioned on some sort of end goal. But one of the things that we were looking at was, again, specifically thinking about how we can take these sort of model-based approaches and some of these sort of nominal physics-based methods and combine it with some learning so we can get a better prediction. So we'll talk about the method that we chose to generate these pieces here. But again, note that this is something that is very generalizable that you could technically use with basically your favorite prediction method or whatever is state of the art at the time. Okay, so one of the things that we, again, wanted to do was think about how we could start first taking into account the goals of our agent. And this is something that is not always trivial to do, but it is very nice and structured if we are looking at something like a physics-based model. So one of the things that we started looking at was the generalized potential field approach, or very similar to the social forces method. But what's nice about this is basically you have a set of sources that can represent obstacles or the edges of the map. This can basically stop your agent from sort of going into those. It generates a repulsive force and a set of sinks that represent our goal. So this makes it very easy for us to say where our sort of intent lies. And we take these basically different forces that sort of are pulling our pedestrian toward them or repulsing that pedestrian away. We can come up with this very nice linear state space model that basically we can fit to human data and whatnot. So there's been a lot of evidence that shows this actually works pretty well here. So while we can fit this to some human data and we can capture it relatively well, if you look at this, this sort of line here that's produced, even though it captures that intent well, it sort of is constrained well by our goal, and maybe it's fit relatively well to human behavior, it doesn't look very human-like. So it doesn't really pass the eyeball test and whatnot. So this is where those sort of pattern-based methods really shine. So they're really able to sort of capture those more nuances. So to show that a little bit, so let's say this is our full human trajectory. So this is basically this trajectory that we want to be able to capture. We have that sort of nominal model. We are going to get something that's quite likely very similar to this straight line. Again, captures the goal, perhaps doesn't really capture the sort of nuances or the trends of human motion. If we were to take some baseline learning-based approach, we would get something that actually does sort of capture the trend or that sort of nuanced motion of that human behavior quite well. So kind of naturally sort of follows this curvature and whatnot. However, it does not capture this sort of constraint very well. So even if you give it that goal orientation, in general, it's quite hard to sort of capture these sort of constraints or these firm goals into the learning process and whatnot. So our big idea here was to try and see if we can combine these two methods together by using something that can take in this nominal prediction and try and warp it to capture these nuanced sort of human motions and these things that are a bit more typical. So we basically wanted to adjust and sort of figure out how we can sort of push this linear, or again, we'll call it a nominal model, to capture more of this sort of human-like behavior and whatnot. So what's nice about this is this also kind of captures a lot of the things that we typically think about in learning these days. For example, this lends itself quite nicely to things like residual methods and whatnot. And we can kind of think about how this connects to sort of typical trajectory prediction and whatnot. So typically when we have a trajectory that we're trying to predict, instead of just trying to sort of get these values globally, we often look at the displacement between the different steps along the way. And this has been shown to help sort of unify the output and makes learning a little bit more stable. Since we're kind of thinking about this more of this warping, so again, taking this nominal method and sort of pushing it towards our goal here, or towards that examples that we have, we sort of further get that sort of unified distribution over our data, and we kind of just have this sort of offset here instead. And again, as I mentioned, this lends itself very nicely to residual methods. Here, where we can pass in our nominal method, and we're basically trying to learn basically this offset here. So we're trying to augment this trajectory, basically just push it towards this. And again, what's really nice about this is we do get lots of the nice properties that you get with residual learning. So it tends to be more stable and whatnot, and you tend to do no worse than the nominal trajectory here. So this is something that's nice. Again, it captures some of those things that we talked about before, which at least feel good and whatnot in terms of sort of pulling in some of this learning-based components, as well as capturing some of this model-based approaches as well. And of course, we have our sort of number results and whatnot, so we tend to do better with than our baselines and whatnot here. One of the key things I'd just like to point out here is that so because we're using this filtering framework, is we can get a sort of nice distribution out, similar to a lot of other approaches, like so the social GAN, which kind of pushes, gives you a distribution of trajectories out and whatnot. But what's nice about this method, or our method, is that because we have this basically this intent inference, as well as it helps you basically say like where in this distribution you should actually sample from. You get a little bit more structured insight of the distribution over all the trajectories that that you are producing here. Okay, so overall, it seems to work pretty well. And whatnot. But one of the sort of more important things is really thinking about how we can, connect this to a real vehicle and whatnot. So what's nice is this does fit in nicely to our stack that we deployed on our very tiny autonomous vehicle here. So we have our pedestrian intent estimation and prediction here. And what we're going to show in just this very tiny little demo here is we can connect this with reachability analysis of the vehicle itself. And we can use this to inform some decision making that basically tells us whether or not some actions that the vehicle can take are good or bad here. So then we can actually deploy this. We can have this as sort of a safety check. And so by doing this inference, checking this with basically the estimate of what the vehicle is going to do as well, we can see that this is crossing. We can use this as sort of, again, this sort of safety check to control the vehicle here, whatnot. So a little demo on hardware here. So one quick note here, you can actually see in this In this plot here, we actually have two different predictions that are going on. So we both have the prediction of this human, which is basically represented by this line here. This is the human that is crossing the way. We also have this sort of tube that is coming out of, basically that's showing the motion of the vehicle as well. So if we go back just a little bit here. I mentioned that we're using sort of this pedestrian intent estimation and prediction, as well as reachability analysis here. So this is sort of two different methods of prediction that we have going on here. So when we're thinking about modeling these humans, one of the things that we were really thinking about is how can we capture this sort of nuanced human data. Humans, as they're walking around, are very unconstrained. So typically these sort of data-driven methods, even if they have some structure like we did, I typically do better. But when we're thinking about the vehicle and we're really trying to think about safety, trying to do a similar prediction type method didn't really make sense. So we use this sort of reachable set and this sort of reachable approach to also give this sort of prediction in time to sort of help us give some foresight. But we do it with a bit more structure. So given that we know the physical model of the vehicle, and we know some pretty good estimates of the uncertainty around that the vehicle could encounter, which is usually fairly constrained for a relatively robust vehicle. We can actually generate these sets, which have some sort of safety guarantees and are much more accurate in actually capturing the behavior of the agent. So they kind of become more of a fail-safe. So when we actually go to deploy it, we have some guarantees, at least on part of the system, and we're taking hopefully some back check by the human as well. And that leads us to this, just a quick little side note on different predictive representations. So often when I think of predictions, I sort of put them into two categories. So the first is what I call informative models. And this is typically what we think of sort of nominally. So we want to think about our vehicle or our agent, and we want to sort of see a single trajectory. This is fairly intuitive. It feeds nicely into control and whatnot. And it sort of is a little bit more intuitive and whatnot. And you can also add some distributions over this, but nominally, again, you have some nominal behavior and some sort of known or assumed distribution over the data. And this is nice. It's fairly structured. Even if it's data driven, it sort of has some nice form and whatnot. And this is highly informative. The problem is it's hard to get many guarantees on this, and it's you often are optimizing to sort of minimize errors, but it's not clear if these are going to be sort of right or wrong, and the chances of actually hitting, this exact trajectory are basically zero. So you're going to sort of get some errors no matter what. So this is sort of one way to think about it, and this is typically how people do. But there's also sort of another set of predictions that you can think about. For example, these sort of robust models, where you try to think about sort of propagating these the states forward in time. So again, this is tying back to this idea of reachable sets. So you think of all the states that the vehicle could reach in some time horizon. And this basically gives you sort of this bound on where the vehicle could go. And again, it typically is a little bit more certifiable and whatnot. And there have been methods to basically try and shrink this down to make it a little bit more intuitive and less over-conservative than the traditional approach. So I won't go into those details, but that's more of an aside. Depending on sort of what sort of assumptions you want to make, and different approaches for different things sort of work in different ways. Okay, so that's basically all I had to say about that piece so far. There's been lots of sort of follow-on work, really thinking about how we can incorporate other things into motion prediction, for example, different traits, or think more about the different inputs and representations sort of the world, for example, the influence of different agents, and think about how that can help guide motion prediction as well. But sort of building on some of that last topic here, I was just going to spend a few minutes talking about some work that we've been thinking about with occupancy grids. But before I do that, are there any questions or any things that can't wait till the end?
Yep, a question.
Yeah.
For example, when you're talking about intentions, what intentions really can be used. For example, for pedestrians, you are using end goals like positions, end positions. For example, what could be intentions be more semantical ones like changing lane, for example, for car or something?
Yeah, that's a great question. And so in this example that we were showing, we basically predefined them to be that way. And actually, if I go back to one of the example slides I showed, we'll go back back here. Yeah, in general, intentions are things that can be basically any goals, or again, they can be these sort of higher level abstractions, like you mentioned, the sort of lane changing and lane keeping. Those aren't necessarily positional goals, but they do sort of describe some sort of action, and those can work as well. And that's like some of the more common approaches as well. Another thing that some folks have kind of done the in between of this, where you can do things that are kind of both spatial and also sort of high level. So for example, instead of saying a lane change and have that just sort of refer to maybe like a template action or just sort of switching lanes, you can define it then spatially, for example. So for example, in this middle piece, a lane change would be defined as some region behind the car in the next lane. So you do still give that goal as well. So you can kind of have a combination of the two and whatnot.
Mm-hmm. So, and from your point of view, what could, for example, can be the difference between pedestrians and cars in terms of intentions? For example, is it better, for example, for cars to use, I don't know, like high-level interactions like lane changing or something, and for pedestrian to use simple end goals like X, Y positions?
Mm-hmm.
From your point, what is better to use here?
Yeah, that's a great question. Yeah, I think because pedestrians are much more, or they're much less constrained than vehicles, so they have a lot more freedom of movement. I think doing things that are a little bit more freeform and position oriented, at least in my view, given what I just presented and whatnot, I think makes a bit more sense. But yeah, I think when you're thinking about vehicles and whatnot, I think because they tend to be the like immediate goal isn't as important. I think having this sort of high level action, I think it's both more insightful from a designer perspective. So when you're defining sort of what your intention space is, having these sort of more abstract actions or abstract goals, I think make a lot more sense personally. Yeah.
I see. Thanks.
I have one question. So you mentioned in your intent guided prediction, so you are using particle filter approach. So have you compared to just like nominal kind of like shiftwise goal prediction, like TNT or dense TNT, those stuff? How does this particle filter approach compare to the other kind of
so to methods where you don't have like this sort of enforced inference as well? Is that the question? So methods where you don't have like the enforced like intents or goals, basically, sort of more just standard state-of-the-art approaches.
Yeah, like there's like another line of work which is also doing this goal prediction, right? Like you have enumerate some goals or like very dense goal grid, and then just try to use shiftwise learning, right? Like the ground truth goal, and then just try to estimate the goal distribution on this set of goal instead of using this particle filter approach where you do this evolve. I mean, like you said, it's very fast, but I would assume it will require like a few iterations. And also like maybe a side question is like, how do you select the initial particles? Is it like using some heuristics, or is it randomly select?
Yeah, that's a good question. So when you have this sort of inference method, I guess I'll answer in reverse first. So when you have these sort of inference methods, typically you do have some sort of burn-in time, right? So you need to gather some observations. So there is some sort of time where you have you basically have to sort of come up, or it takes a while to get sort of a good distribution over your whatever you're trying to sort of infer over. I'm fairly confident that we just did a uniform distribution at first, and then did the inference from there. So we did compare to a lot of state-of-the-art approaches as well. So we did sort of approach it to cases that we didn't use any of the sort of filtering pieces and just used sort of this state-of-the-art at the time as well. And I think all the details of all this are in our paper as well. So we did compare to these sort of baselines and whatnot. I don't know if we actually looked at timing though. That would be actually a great question. If Ted wants to answer it, maybe he can drop a note in chat if we looked at timing.
What do you mean by timing?
I think the question was because these typically when you have the particle filtering approach, it does sort of take some time, both I think in terms of just running the multiple iterations as well as sort of the burn-in time.
Okay, latency you mean?
Yeah. Yeah, hopefully that answered your question. Are there any other questions? Okay, so I'll just take I'll just try and take a few quick minutes to just talk a little bit about some of this work in occupancy grids. So we'll skip over a lot of the details and whatnot. But again, one of the things I sort of was hinting at a bit was how when we think about these predictions and whatnot, often the representation can really have a big impact. Even when, as I mentioned, sort of in this slide right before here, you sort of get different insights. You can make different assumptions. You use different tools depending on basically what you want and sort of what this representation is. So another thing we can start thinking about is really changing sort of that, as I mentioned, sort of foundational representation. So moving from things like XY positions or really trajectories and thinking about things like occupancy grids. And this can really help us not just think about, again, thinking how things are going to progress forward in time, which you can obviously still do with things like occupancy grids, and we'll touch on that a little bit. But you can also think about more spatial inference. So really thinking about understanding the space itself and seeing some insights from, if we can pull some insights from human modeling to start inferring things like things that are occluded or things in sort of unknown space. And as I mentioned, this sort of really changes the types of assumptions that we make when we have. So typically, even when we're thinking about, say, predicting, say, another vehicle's motion forward in time or a pedestrian's motion in time, it sort of relies on this idea that we have this sort of object-oriented approach where we take our perception data and we start sort of giving it sort of semantic labels, and we can say, okay, this is a vehicle that I detect in front of us. How are they going to maneuver forward in time? Or again, I now have a pedestrian. How is this going to maneuver? So instead of sort of taking, again, this sort of agent-based or sort of object-based approach, another thing you can do is you can start thinking about the world in terms of occupancy grids. So you can start dropping some assumptions, which have some trade-offs, right? So you lose some insights when you start sort of going to a full occupancy grid approach. But you do sort of get some more generality, and you might be able to handle things that might not be necessarily easy labeled or mislabeled in your detection algorithm and whatnot. So there's a few other nice things about occupancy grids here. So for example, you have one sort of default sort of representation that captures the unknown. So you have this sort of 0 point, so you know you have your free space, which is represented as this blue. You have your occluded or occupied spaces, so you have these sort of things where you know an object is. These are the red. But then you also sort of have a clear understanding of all the things that you aren't getting information about, or the things that you sort of have, again, that are unknown. And that's where this sort of light green is. And you typically get this sort of nice distribution in between. So you have this sort of just sort of given representation that captures the unknown very nicely. The other thing that's nice about this is it does sort of follow this nice sort of image format. So it also lets you use some different types of inference tools. For example, you can start really leaning into things like video frame prediction. So instead of relying on more of the supervised learning type approach, you can lean into a lot more of this sort of vision or sort of image processing type approaches, where you can sort of propagate these forward in time in a slightly different way. Also, depending on the planner that you use, it might be easier to incorporate things like occupancy grids, where you sort of have this grid space. You can more easily define free space and whatnot. So depending on sort of the application, can also facilitate a lot of things. But one of the things that I think is most interesting about this representation, again, is this idea that you have this sort of nice encoding and representation that says explicitly what you don't know. And this is something that for autonomous vehicles is very hard to handle. For example, in this corner, it's very hard to sort of know what could be going on sort of behind the scene and whatnot. And this sort of tells you exactly that you don't know. However, humans, on the other hand, are actually very good at doing things like inferring what's going on, even in areas that they can't see. They're not perfect, but they are pretty good at it. So for example, here, this is a case where hopefully this video is playing kind of nicely. This pedestrian sort of pops out from behind a car, and this vehicle that we're watching from the dash cam actually starts braking before this pedestrian pops out, despite the fact that they have a green light and everything looks basically all good. But that's because they observe this truck that's just to their right, and it comes to a stop. So they observe something happening that sort of triggers this insight or this flag that something isn't right. And sort of, again, they can sort of get some of these cues on this. This isn't always perfect. Just for fun, this is an example of where it doesn't work out and there is a very near collision. So people are not always good at this, but they are usually pretty good. So one of the things that we've been thinking about is, again, thinking about how we can use this occupancy grid representation and try to, again, also take advantage of human insights to start inferring things. So the basic idea is by observing some agents around us. So if this red vehicle is, say, our autonomous agent, by observing vehicles around us, can we start making inference about other agents or the environment around us in an improved way? So can we sort of start leveraging these agent behaviors and, again, start sort of informing what we do with the environment? And so I'll skip over some of the details and whatnot. But the basic idea is we want to basically learn this mapping from inference techniques. We basically want to see if we can incorporate human models into it, so we can basically have this better inference about what is going on. So instead of just sort of assuming that we always have no information, we can start sort of making inferences, seeing sort of what this agent is doing. So as we see them, say, stopping or slowing down, we can start inferring that there may be a pedestrian in front of us. And this is sort of a simplified example. Things can get much more complicated when you look at sort of real data. Again, you try to sort of start understanding how people drive in relation to this sort of occupancy grid maps and modes. But it can do some pretty cool things, like it can help inform if there's oncoming traffic, for example. So instead, again, of saying we just have no idea of what's going on in oncoming traffic, we can start making inferences that, okay, there's likely an object or another agent in this spot. So we probably should not go ahead and make this right turn and whatnot. So then we can do things like wait for cues, like this agent is moving, there's likely a free space, and so we can go ahead and make this turn and whatnot. So again, I know that was very fast, but again, if we think about different representations, it can kind of lend itself to different types of prediction, different types of inference, and hopefully can sort of help inform more broadly different types of interactions and help inform sort of what actions are valid and hopefully lead to sort of more safe things. So again, that's basically all I had prepared today. I'm happy to chat about any of the things that we talked about or anything else here. I'd like to sort of give a shout out to all my students who worked on this and the sponsors as well. And again, thank you for having me. So I'll take questions if there are any more. I know that last bit was very fast.
Hi, Kelly.
Katie, yes. Can you hear us?
Yes.
Okay, great. Also, the question about occupancy grids. For example, when we are doing, for example, usual motion prediction, we can leverage the information about ID of some object. So we can, for example, reason about their future, I don't know, forecastings. But when we are talking about occupancy grids, it's sort of, I don't know, we can lose this ID information and just, yes, we can, of course, we can clearly see, for example, the regions where we can go, the regions where we cannot go, something like that. But what do you think about the losing of this ID? Can it really damage our prediction ability or not?
Mm-hmm. That's a great question. And so on some level, you do lose ID information often. There are some folks who've tried to do some things where it's not quite occupancy grids, but they've tried to use image representations. So for example, instead of having an ID, you could have like a color code attached to that agent in sort of this visual representation. You can use that. So there are some things that kind of look at that instead. However, maybe I'll comment on this in two other ways. So first, so yes, you lose some IDs information, but sometimes that's a good thing. Well, I guess it depends on how good your tracking algorithm is. So if you ever have any issues with ID swaps and whatnot, having a representation that doesn't rely on them can actually be very useful. So this was a few years ago now. But one of the things that we had worked on before was looking at controlling a vehicle in an intersection. And one of the big issues we actually had was in ID tracking as there was lots of crossings and whatnot. And so one of the things we did was we moved to occupancy grid approaches because it wasn't relying on these tracking ideas. And that sort of made all the decision-making downstream tracks actually a lot easier. So that's just sort of one example, but depending on the approach, sometimes it's actually a good thing. The one other thing I might show is, depending on your application, one of the things that we were using this for, let me see if I can go to my slide really quick, is we were actually only using segments of the occupancy grid to sort of combine things together. So let's say we have a situation like this, where we have some detected agents and say we can actually tag them as like ID1 and ID2. They each have some environments ahead of them that is sort of going to give us some information. And we have our occluded areas. So this is basically the regions that this agent can't see. So again, this is sort of specifically looking at the inclusion problem and whatnot. So in this case, we're still using the tags to sort of get different areas that we're trying to pull from, and we aggregate it all together. So we're still doing things like tracking this agent to get some information about what is going on in front of them and pull that information, but we're combining it all together in an occupancy grid. So it doesn't have to be sort of all one or all the other. You can kind of leverage both. Yeah, so that was a few different ways to answer your question. Did I actually answer your question?
Yep, thanks. Also, a question maybe a little bit off topic, but you just briefly mentioned in the beginning of your talk about this adversarial examples for the in fact motion prediction or any, for example, tasks connected with motion. How do you think on the real stage of I don't know, of research for autonomy, does it make sense to deal with adversarial examples? I mean, for behavioral adversarial examples, for example, when we can get the hardest behavior of the objects on the road?
That's a great question, actually. And this is when in my initial sort of presentation, or like the start of my presentation, when I was talking about sort of the robust approaches and whatnot, most of those do sort of look at these like worst case examples. And it's not clear if that's necessarily the right thing, especially when you're thinking about working with people. It can really lead to sort of poor poor edge cases and whatnot. So I think the also, and I might be going on a tangent, so please stop me if I'm not actually answering your question. But there's a few things to think about. So I think it's probably not useful to always take the sort of worst case or really look at the full adversarial examples, but it is very useful to sort of know where you have flaws in your model and sort of where these holes do pop up, especially in relation to people. So unrelated to the stuff that I talked about today, some of the work that we've been doing is on finding failure cases and sort of finding these worst case examples, specifically looking at sort of where models of behavior can break down and whatnot, or sort of where you could have holes there. And that's something, it's insightful from a design perspective, but it's not necessarily clear if it's something that's good to sort of actually incorporate back into the learning method, because again, you could basically get into this case where you learn that it's best to just always stay inside and never go out and interact with people, whatnot.
So am I correct that the proposal is the following, could be the following, to have sort of additional evaluation set with such sort of worst cases and to inspect from time to time, for example, how the models behaves in fact based on these worst cases?
Yeah, I think that would make sense.
Mm-hmm. Thanks. By the way, yes, maybe also the question from my side. Sorry, guys. Yes, when we are talking about this incorporation of physics for the particles models in this prediction task, whether, for example, I think we already asked, yes, about it, the comparison with current state of the art. How do you think, for what types of the objects it makes sense most? For example, for pedestrians, for cars, for cyclists, or for example, where we have, for example, quite predefined laws of motion as for cars, or just, for example, for pedestrians that is quite chaotic, in fact.
Yeah, so just to make sure I'm understanding your question. So the question is sort of where does this sort of model or framework really make the most sense?
Yep.
And for what types of agents?
Yes.
Yeah, I think you make a very good point, especially for things, for agents that are a little bit more constrained by things like, well, technically, I guess anyone who's on the road is constrained by the rules of the road, but pedestrians are a bit more freeform. So I think things like this becomes very important when you're working with pedestrians, especially because they don't have as many sort of kinematic or dynamical constraints and whatnot. For things like for vehicles, I think, as was sort of mentioned by one of the questions, I think if you have, it probably makes more sense if you're looking at different types of intents and whatnot. And for vehicles, one of the other challenges is you, chances are you're not around them for that long. So you might need different methods where you don't have to sort of have this burn in or have some sort of inference thing where you're trying to do this sort of long-term prediction. So if you're only going to be having an interaction with a vehicle that lasts something like 10 seconds, looking at something like this that really, again, it excels at sort of these longer term predictions might not make sense. So I think that's sort of the trade-off to make there.
I see. Thanks.
Thanks, Catherine, for the presentation. My name is Brian. I have a more high-level question about the trajectory prediction evaluation. So we have been seeing, like in the academia, people have been using the displacement error, like the trajectory prediction displacement error, right, as the evaluation metrics. And apparently, you know, when we were able to reduce the error from like social force, like 4 point something, to like the current methods, which are usually 1 point something, that's a very meaningful improvement. But I think currently when we're only improving a little, and and sometimes we are just improving on some samples and actually regressed on the other samples. And when you compute the mean, it's a slight improvement. And I wonder how valuable that is, and if there are something in the academia that is going on to make the evaluation more valuable, or more representative. And also related to this question, like we always care about how we want to use our prediction. So I think maybe it makes sense to do some end-to-end evaluation. So when we make prediction, we want to evaluate how it affects our motion planning, and eventually how it reduces our collision rate or something. So I wonder if that's also something that academia would consider for evaluation.
Yeah, that's a great question. Yeah, so maybe to answer them one in a row. Yeah, I think you are totally right on the sort of evaluation thing. And let me see if I have a backup slide on it. I used to have a slide. I don't think it's in this deck, but yeah, if you look at like the actual like increments in the gains for the past few years in the prediction methods, it's a very small change. And even the baseline methods, like I think you mentioned, like the social forces and these sort of nominal models actually do work pretty well. So we're adding a lot of machinery and adding a lot of sort of heavy duty stuff. And the question is it actually worth it? And sort of what is the ultimate goal? So I know that there are quite a few people who are looking explicitly at different ways to evaluate the trajectory predictions and whatnot, especially in that you can have a prediction that seems very reasonable and seems very good, but might throw high errors, which really it's hard to know if like a reasonable prediction is good or not without sort of knowing the actual application. Like if you want something that's safety, you never want to have that just a reasonable prediction and whatnot. So there's a lot of discussion about it and whatnot, but at least I personally don't have any like immediate sort of like, here's the solution to the trajectory evaluation problem, other than I know it's a hot topic and a lot of people are thinking about how to address it. But in terms of how to really see how these sorts of impacts or like modeling errors and things like that affect your downstream tasks, sort of again, something I didn't necessarily touch on today, but one of the things that we've been working on in my lab, and I think a lot of people have been sort of starting to talk about as well, is thinking about ways we can do some sort of validation and very easily sort of change modules and see the impacts of these. So we've been working on some validation tools where you can basically control how much uncertainty or how off your model can be, and then we can see sort of what are the effects as you sort of look through the whole system and whatnot. So if you have a reasonable simulation of your system, which for driving type applications is usually not too bad, then you can sort of see, again, as was mentioned in a previous question, you usually, when you do validation, whatnot, you tend to get sort of worst case analysis and whatnot, but it does kind of tell you sort of where the bounds are. And as you sort of change the effectiveness of your model, your expected errors, you can kind of get a reasonable estimate of where and how your system will fail, whatnot. Did that answer your question at all?
Yeah, I think that basically aligns with my understanding, and yeah, I think that's great. Thank you.
Yeah, but happy to share those papers or talk about that some other time too, since I know that was sort of a vague description.
I have a high level question, which is, you have two topics here. One is like predicting the XY at certain timestamp, and maybe like some associate variance. Like this is, like probably the mainstream approach for prediction in the past few years. And now it seems like people start to look into this occupancy grid or like flow kind of approach on the image space. What do you think is like the pros and cons between these two? I mean, like it seems like the occupancy grid is like the new trend, but like, what's your opinion between like, I mean, for the pros and cons between these two different representations?
Yeah, that's a great question. And I think as with most things, I think the hardest part about human modeling is, or I guess any modeling type framework is people will, argue that whatever they're doing or the sort of most current thing is the best one. But I think if we go back to maybe, where's the slide? So this is the sort of image I typically think of, and sort of how I would categorize things. I hope you can still see my slide and everything. Also, I don't know if you could see my mouse at all, but
Yeah.
Yes, we can.
Oh, great. But I think, so even though this picture is more of this sort of general set-based approach, I think the occupancy grids are very similar in essence. I think the trade-offs are, again, depending on the type of planner that you're using, when you have either, distribution over trajectory or sort of again, like XY position, it is more informative. Like it gives you a little bit more constraints. It's a little bit more direct on how you can apply it into control, again, or your planner, depending on the type of planner. But it's a little bit more insightful. So you get a more precise estimate. There's more that you can like really concretely say about a prediction that looks like this. Whereas if you have, again, I call it a robust model, but in general, if you have the sort of set-based approach, the nice thing is you have usually a bit better estimate of the uncertainty and the different possibilities. It's a little bit easier to capture things like multimodality and things like that. So it typically gets like better coverage over the possibilities of what could happen. So in some sense, it does a better job capturing what's going on, but it is very easily over conservative, I think. It might not be quite the right word, but it will tend to over approximate or sort of give you too many possibilities. And typically that's then at some point you have to sort of reduce down what you actually choose or what you actually use when you're going to actually deploy your system. So for example, for an occupancy grid, you get these values between 0 and 1. At some point, you have to pick your threshold. So like, what is the likelihood that there is an object here? And sort of what are you going to choose from? So you kind of have to sort of set your risk a little bit more concretely in that sense. And part of it is you set that basically when you're trying to get something that is more useful. So at some point, like you want to get like a smaller set, so something that seems more reasonable. In many ways, something that is closer to this type approach. So I think the pros and cons, I think, are more down to you get a little bit more flexibility in these sorts of approaches, be it occupancy grid or these sort of set-based approaches, but it's hard to sort of set where and how much sort of freedom you want to give it, if that makes sense.
Okay, thanks. So so what you said is like maybe depends on the planner, like what type of planner that we use. And say, for example, like you mentioned, like in the second graph that you have a single, single prediction, you have like covariance at each timestamp. I mean, like I think like that one, you can also have like multi-hypothesis, right? And then for each of the hypotheses, you can also have like this covariance. And I'm just wondering, like, say, for example, if you using the covariance, and then you can also plot out this occupancy grid using that, right? And you have like multiple hypotheses, and then each of the hypotheses maybe have like some probability, and also at each timestamp you have like this covariance. So in some way, you can also infer like the occupancy grid with that kind of like multi-hypothesis prediction with covariance. But maybe is my understanding like maybe in that way, because your covariance is assuming some like Gaussian distribution or those, so it's restricting the flexibility, while the occupancy grid type of thing, like you don't have those kind of constraints, so it's a little bit more freeform, and you can hopefully like represent the more complex distribution.
Yeah. So the challenge with the occupancy grid, so it also depends on how I guess how like strict you're sticking to the actual original formulation too. So because on some level you just want a representation that covers like the uncertainty over space, right? So you can take any sort of distribution, say like this, and it can be multi-hypothesis as well. And you can convert it basically to an image where you sort of represent your uncertainty over the space and whatnot. So you're basically coming up with an image representation. If you're looking at a occupancy grid, it really is looking at like what's the probability that each cell is going to be occupied and whatnot. And typically you are assuming that they are independent as well. But there's no real reason for most applications to really stick to that like strict formulation and whatnot. So, so for making like image representations, then that's a relatively straightforward way to basically represent your uncertainty here, and it does sort of have some semblance to that as well.
Yeah, thanks.
Any other questions, guys? If not, let's thank Katie for the insightful talk.
Thank you. And again, thanks for having me and for taking the time to chat.
Thank you for your talk. In fact, it was really insightful.
For the talk.
Thanks.
Thank you.
Thank you.
Thank you. Bye.
Mhm.